Random numbers are really important in computing, but it turns out that computers aren't very good at generating them. In this video, we'll explore why that is and how random number generators work. Fundamentally, computer algorithms, when given the same input, should always produce the same output, which makes them predictable and what we call deterministic. However, this is not so great when trying to generate random numbers because randomness is inherently unpredictable and what we call non-deterministic. So how can we use inherently deterministic machines like computers to generate random numbers? Well, a common way is to fake it and get something that looks random enough for your application. A pseudo-random number generator uses a source of initial randomness called the seed and expands it into a much longer sequence of numbers that appear random but are actually deterministic and repeatable if the seed is known. If you play Minecraft, you might be familiar with the concept of a seed. In Minecraft, world generation is based on seed value, and the same seed will always result in the same world. More on Minecraft later. So how are these random seeds for pseudo-random number generators chosen? Well, a common classroom example is using the system's current time, which is the time in nanoseconds since the computer was turned on, because this value is usually unpredictable and constantly changing. There's also true random number generators, which are not seed dependent nor require any sort of input, instead using physical events that are unpredictable to generate randomness. For example, mouse movements, keyboard strokes, or electronic noise. According to their website, the Singaporean office of a company called Cloudflare measures the decay of a pellet of uranium to generate random numbers, which is a spontaneous random process. Some systems use a combination of both pseudo-random number generators and true random number generators for robustness. For example, that same company, Cloudflare, also has a lava lamp wall and claims to use images of the current state of the lamps as part of their seed, since the lava goop never takes the same shape twice. Okay, now let's talk about linear congruential generators, which are one of the oldest and simplest types of pseudo-random number generators that generates random numbers through a mathematical formula. So I've pasted the formula into a document, and if this looks complicated, just trust me that after we walk through an example, you'll see how straightforward it is. So if you're not familiar with mod, it's basically the remainder after dividing one number by another. And what we're doing here is we're taking the current seed, and then we're doing a bunch of different things to it to get the new seed. And in the next iteration, we're going to use the new seed in replace of this. So I tried to simplify this, and hopefully it didn't make it more confusing. But what we're doing is taking the old seed, doing some stuff with constants, and then getting a result that is going to be the new seed for the next iteration. So let's run through an example with real numbers. Okay, arbitrarily for the constants, let's just let a equal 3, c equal 2, m equals 5, and x sub 0, which is the first element of the sequence, let's just give it the value of 1. So then for n equals 0, what we can do is plug in our constants into this formula. And x sub 0, remember, is 1, so I'm just going to quickly plug that in. So then 3 times 1 plus 2 is 5. 5 divided by 5 has no remainder, so 5 mod 5 is equal to 0. So now we know that x sub 1 is equal to 0. Okay, for the next step, where n equals 1, remember we're going to take what we calculated in the previous step and plug it in as the seed here. So x sub 1 we calculate is equal to 0. 3 times 0 plus 2 is 2. 2 mod 5, well, 2 divided by 5, the remainder of that is 2. So the answer to this is 2. Now we know that x sub 2 is equal to 2. For the next step, n is equal to 2. And then we plug in everything. Remember, we calculated x sub 2 in the previous step, so we can plug that in. 3 times 2 is 6, plus 2 is 8. 8 divided by 5, there's a remainder of 3. And so we know that x sub 3 is equal to 3. For the next step, we're going to plug in again what we previously calculated. 3 times 3 plus 2, that is 11. 11 divided by 5, well, the remainder of that is 1. And now we know that x sub 4 is 1. And you might notice something interesting. That was actually what our original x sub 0 is equal to. So together we calculated the first couple numbers in the sequence, but I went ahead and did a couple more. You'll notice that the sequence goes 1, 0, 2, 3, 1, 0, 2, 3, and presumably 1, 0, 2, 3. The sequence is repeating itself. So linear congruential generators are fast and memory efficient, But as we saw, one limitation is periodicity. The sequence of numbers is going to repeat itself. So in our demo, I purposely chose small numbers, but in the real world, you're probably going to choose much larger values for the constants so that the periods are larger, meaning that the sequence of numbers that repeats itself is much larger. And you might choose some numbers like this. So where did I pull these numbers from? Well, Minecraft. Nearly all of Minecraft's randomization is computed through Java's pseudo-random number generator, which utilizes a linear congruential generator. Cool, right? This is actually from the paper proving that Dream, a Minecraft content creator, cheated during his Minecraft speedruns since he was essentially impossibly lucky, getting higher than usual drop rates for items. If you're interested in reading it more, which I recommend, the paper even shows how the linear congruential generator is used in combination with the computer's system time, using special operations to produce a seed. And who said we would never use computer science or math in real life? A more modern method of generating pseudorandom numbers compared to the linear congruential generator is called the Mersenne twister. Look it up if you're interested, but it basically produces longer sequences of numbers before repeating, and its randomness quality is higher. So now that we understand all these different ways to get random numbers, why should we care? Well, if you're a gamer, randomness plays a huge part in how lucky you are in a game. And if you understand it, you can potentially manipulate it to your advantage. For example, if a game uses player input as part of its seed for generating random numbers, tool-assisted speedrunners can reverse engineer the game's random number generation functions to pull off frame-perfect runs. This creator made a great video about how RNG in different video games works and how people have been able to exploit it. Other uses are in cryptography, which is definitely the driving force behind why there's such continuous advancement in this field. Here, the unpredictability of these numbers is crucial. If a hacker can predict the random numbers used in a cryptographic algorithm, they can potentially break the encryption. Every time you make a secure online transaction, send an encrypted message, or browse a website protected by HTTPS, you rely on the strength of the cryptographic algorithms and the quality of random numbers to ensure the confidentiality and integrity of your data. Beyond cryptography, random number generators find applications in various fields. In finance, for example, they're employed to model different market scenarios and estimate the probabilities of specific financial outcomes. The Black-Scholes model, used for pricing financial derivatives like stock options, relies on randomness as a core assumption to make predictions about market behavior. And that's just the tip of the iceberg. Random number generators serve as the backbone of various systems and processes that require fairness, unpredictability, or simulation of real-world phenomena. From gaming and financial simulations to scientific research and data analysis, random numbers continue to be a foundational element in our increasingly interconnected world. I hope you learned something new from this video and subscribe if you did.